As I said before in the first video, I'm in a bit of a time crunch here, so I'm going to go ahead and get started. No plexers. No one says anything about those anyway, so maybe you guys don't care. Example number 2. Oh, by the way, here we are, motion page 2, or if you look down at the bottom of the page, you should see a number 76 down there at the bottom. It's page 2 in our packet, but 76 at the bottom. So example number 2, we're given that a particle is moving along a line, horizontal line, position function, we always need that, or we need something that gives us some information about the motion of this particular particle. And we're going to go ahead and figure out what the velocity function is. Now, given that the position function is t squared minus 4t plus 2, remember the velocity is the rate of change of the position. So velocity being rate of change of position, rate of change being another way to say derivative. So the velocity is the derivative of this function here, and the velocity derivative of this function with respect to t. Just like if this were an x squared, the derivative of x squared would be 2x. The derivative of t squared would be 2 times t. Okay, and then we take the derivative of the next term. The derivative of negative 4x would be negative 4. So the derivative of negative 4t would be negative 4. And then the derivative of 2 is always 0. The derivative of any constant is 0. And so we have the velocity function is equal to 2 times t minus 4. And the acceleration function then would be the derivative or the rate of change of the velocity function. So a of t is v prime of t. And if you really wanted to, you could write that as s double prime of t. So all of these three mean the same thing. A of t, v prime of t, and s double prime of t. They all mean the same thing. Anyway, the acceleration being the derivative of the velocity. The derivative of 2t would be equal to 2 because this is just a linear function. The velocity is linear, so the derivative of a linear function is just the slope of the line, and that's 2. So it says here the acceleration is always equal to 2, so the acceleration is constant even though the position is not constant. That's okay. It's like acceleration if you... I'll get to that later. I don't want to overwhelm you because there's so much here. This is the basics of straight line motion. So you're learning some good stuff here. Let's complete the chart for the first 5 seconds and show where the object is on the number line. Okay, so the position at time 0, if you plug a 0 in for t, we get 2. And I'll let you do those computations, okay? There's not a whole lot of room here, but we did the position in the last video, and I'm going to bring the position function over here so it's easier to see. S of t is t squared minus 4t plus 2. Okay, so let's do the position at all these different times. The position at time 0 is 2. So here's the object. I'm going to put it right here, right underneath it. Position at t equals 0 is 2. The position at t equals 1, 1 minus 4 is negative 3, negative 3 plus 2 is negative 1. So the position is negative 1. That would be at time t equals 1. And then at t equals 2, we have 4 minus 8, and negative 4 plus 2 is negative 2. So we have the particle then is moving this direction, and this is at t equals 2. Okay, so the particle is going like this. And then at t equals 3, we get 9 minus 12. 9 minus 12 is negative 3. Negative 3 plus 2 is negative 1. So somewhere along here, it doesn't have to be necessarily at t equals at negative 2, but somewhere here, maybe it goes past that. But nevertheless, it kind of turns around, and it's right back here at t equals 3. And at t equals 4, we get 16 minus 16 is 0 plus 2, and that's 2. And so it continues on here, and it's back here at t equals 4. And then at t equals 5, we get 25 minus 20, which is 5. 5 plus 2 is 7. And so it cruises all the way over here, and it's at now 7 when t is equal to 5. Alright. Well, you might be able to guess here that the velocity in between 0 and 1, and then 2 even maybe, is going to be negative. Okay, so anyway, we cruise right over there to 7 at t equals 5. But let's just take a look. The velocity at time 0. Now we're going to plug in 0, into the velocity function, and that gives us that the velocity at time 0 is -4. Velocity at time 1 is 2 minus 4, which is -2. So we're still moving in the left direction. So we're moving left at t equals 0. Initially we're moving left, and then at t equals 2 we get 0. So it just so happens that at t equals 2, at this point is when the particle stops. And so I showed this little curve like here, but what it really does is it goes over to the left. At t equals 2 it stopped, and then it starts going backwards. It starts going backwards or to the right after the t equals 2 mark. Okay, and so in t equals 3 we get 2 times 3 is 6 minus 4 is 2, so the velocity is positive. And so again we're moving to the right. That's why we are able to come back here, and we can see, hopefully be able to see, after t equals 2 the velocity will always be positive, because when t equals 4 we get 4, when t equals 5 we get 2 times 5 is 10, minus 4 is 6. And we can see as t gets bigger, the value of the velocity is just going to get bigger and bigger, so therefore this particle is going to continue to move to the right, because the velocity can never get back to negative or even back to 0. It's only 0 one time. Okay, so I know this is a lot to kind of process here, but nevertheless, if you can fill in the chart, the concept will come, and maybe you already have it, but just be patient. Be patient. It's not going to happen overnight to many people. It doesn't just happen. You just have to be patient. And it says, let's go ahead and fill out the chart here for the absolute value of the velocity, which you should recognize that to be the speed. And the speed is just always either 0 or a positive number. It's the same as the velocity, but as a positive number or 0, as you can see here. So speed is always positive, like a radar gun. If you hold a radar gun, it's not going to show a negative number. Okay, and the acceleration, no matter what the time is always 2. Okay, and again, we'll get into some more detail in the class when we see each other Thursday and Friday. So the description of the particle's motion: moving left. Okay, I mean, you're moving left, and we can get into speeding up and slowing down, but we are, in fact, maybe this is not intuitive, it's usually not, but if you're approaching a stop, I'll try to help you understand this, and we'll talk more and more about this, but let's talk about this. If we're moving left and we're approaching, notice here our speed is decreasing. Our speed is decreasing from 4 to 2 to 0. Then we're slowing down. Slowing down. Okay. Same with at t equals 1. We're still moving left, but we're also slowing down. I got a really neat visual, like I said. Please remind me in class to do the visual on the speeding up and slowing down. That's a fun one to do. And then over here, the position is at -2, but the velocity is 0, speed is 0, so we're stopped. Okay, and then after that, we're moving to the right and we're speeding up. See how the speed is getting bigger, getting higher, and again, so right and moving, speeding up. So at every time after 2, we have moving to the right and speeding up. Okay. So I'm going to go ahead and pause the video. No, I can't. I can't do that on the computer. So I guess I'm not going to pause it. I was going to read this next part here. Let's see if we can work through this together. It is too much work to do such work for complicated functions. Okay, I agree. We are generally interested when the particle is stopped or when it has no acceleration. We're also interested when the object is speeding up or slowing down. Maybe I already jumped the gun on that. Realizing that an object's velocity is either positive moving right or negative moving left or 0 stopped, and an object's acceleration positive or negative or 0. Okay, we can now use a chart to determine all the possibilities of an object motion if you were looking at it from above. Well, I'm not sure, since I didn't make this worksheet, I'm not sure what the author of this had in mind, but what I will do is just go ahead and fill it out how I see fit. If the acceleration is positive, and like I said, acceleration is how you push, so we're pushing to the right, pushing right, pushing left and not pushing at all. Not pushing. It doesn't show us an acceleration of 0 in the other example. Okay, moving right, moving left, and stopped. So if you think of, again, velocity is moving, how you move, acceleration is how you push. If the pushing and moving are going in the same direction, then we're speeding up. Speeding up. Pushing and moving in the same direction, we're speeding up. And then not pushing at all and can't be speeding up. It's not pushing and not moving, so you're stopped. I'm not sure what we should put here. I don't really care about that. But if the acceleration, if you're pushing to the right but moving to the left, you're slowing down. Okay. Pushing to the left but moving to the right, you're also slowing down. This is probably not going to make a whole lot of sense right now. Just fill out the chart and I'll give you a good visual in class, like I said. But use this to answer the questions as well. Pushing to the right but stopped, you're just stopped. Okay, if you're stopped, you're stopped. Alright, so there we go. And again, like I said, I don't know, moving left, not speeding up or slowing down. This I guess would be constant speed. Well, maybe we'll leave it like that, constant speed. I bet that's what he meant. Constant speed if you're not accelerating. Okay, so accelerating to the acceleration positive means you're pushing to the right. Yeah, okay, so enough said there. For example 3, what I'm going to do is, yeah, let me try to squeeze that in here. I won't go beyond my 15 minutes. I've got 3 minutes left. Let's see what we've got. We've got a particle moving along a horizontal line with position function, okay, given to us like the ones before, and do an analysis of the particle's direction, acceleration, motion, all this stuff in position. So the velocity, we can easily do that. We know that the derivative of t squared is 2t, and the derivative of negative 6t is negative 6. And the velocity is 0 at, well, if we want to know when the velocity is 0, then we have to set the velocity equal to 0, and we see that t is equal to 3 at t equals 3. Okay, just solve this velocity equation, set it equal to 0. Make a number line of v of t showing when the object is stopped and the sign and direction of the object at times to the left and right of that. Assume that t equals 0. Alright, so what do we want to do here? If at t equals 0, let's do this, t and v of t. Let's see if we can kind of figure out what we want to do here. At t equals 0, the velocity is negative 6. Okay, at t equals 1, velocity is negative 4. T equals 2, velocity is negative 2. 3, we get 0. 4, we get 2. Alright, so make a number line of v of t showing when the object is stopped and the sign and direction of the object at times to the left and right of that. Not really liking this particular example. Not liking this at all. So, since I don't like this example, I'm sorry I didn't preview this. This is what happens when we don't have books. Normally I go out of the book, but not all of us have books, so I'm trying to use different resources here and still give you the information you need. So what we're going to do is I'm going to stop this video. We are going to not do this example, and that's it. Alright, we'll do the next page, and that'll be the last video. I hope I can get it done in the last video.